me turn this thing on. You can hear me better now. Not that it was a problem before. So I can integrate this. So let's say I go from, P naught to P, dP over P. And, delta H is a constant. We looked that up, in some tables. But now I have this, I have to do this different. I have to integrate 1 over T squared. So that's the integral of T to the minus 2. And remember, what is the integral of x to the minus 2 dx? Yeah, it's minus 1 over x, and if I go from A to B, I'd evaluate that from B to B, right? So that's calculus. So if I do this on the left side, that might be a worse integral, but we've done it a lot. So we recognize that as being the logarithm. And then I have a minus delta H over R, 1 over T minus 1 over T naught. And this is the Clausius-Clapeyron equation. And you can Clapeyron equation. You can use this to you can get out your calculator and do some problems. What this, we can rearrange this. This gives us our formula for P of T, because that's what we really want. We want I'm going to draw a picture. I should probably draw one that's not grossly incompetent. So, we have our P as a function of T. And, let's draw for water here. And that curve there, which is between the liquid and the gas, as a function P of T. And if I use this, it's P naught, e to the minus delta H over R, 1 over T minus 1 over T naught. And it has that you see a lot. You see things that look like e to the minus like delta G over RT. We'll get here to that standard state. This was from general chemistry. I can calculate the equilibrium for a constant, equilibrium constant for a reaction, if I know the standard free energy change delta G. And you did problems like this, and we'll get there too. But it has that same. It's an exponential of an energy divided by RT. And if I actually got fired up Mathematica, and maybe Shaka has you doing this problem, who knows? And give you some numbers, and you can plot that curve, okay, using this formula here. Now, okay, since you're actually here, but this is being recorded, but maybe people don't want to watch the video. Here are some favorite test questions. So this is the kind of thing I like to ask on an exam. Let me draw my picture here. Remember, this is the t-axis and this is the t-axis. Here's solid, liquid, gas. And I'm imagining a process where I go from A to B. Okay, so I take a gas, or I take a liquid and this is we could do it another way. Uh, but at a constant pressure, I take a liquid, it could be water, and I heat it up. I add heat. I'm raising its temperature, and eventually it gets to the boiling point, this point here. And it boils, and then I'm putting heat. Remember what happens there. I put heat in, I have the liquid and I have the gas both together, coexisting at that temperature, and then and I keep putting heat in. I'm converting for a little. I give a little pulse of heat. A little bit of liquid is converted to a gas, and it stays at that temperature until I'm out of liquid. Now I'm adding heat to the gas, and the gas's temperature keeps going up, and then eventually I get to point B. Okay? I do that at constant pressure. Now, graph the following thermodynamic quantities. And you know, there's a whole list of them. Let's start with the molar volume, and then we'll do the entropy, and then we'll do the enthalpy, and then we'll do the chemical potential, and finally we'll do the constant pressure heat capacity. And remember, C sub P is the derivative of H with respect to T at constant P. And so, you know, these are things we've seen. I could just ask you to do this, but the yield would be low, I think, unless you had time to think about it. So let's think about it, because I keep saying this. Everything makes sense, doesn't it? But let's see if it makes sense today. So I'm going from TA to TB, and I'm going to plot. This is the molar volume. And here's the boiling point. So I'll draw a line there. So I have a liquid. I heat it up a little. I start here. If I heat a liquid up, what happens to its volume? Yeah, so it slightly increases, doesn't it? Right? Like when you heat things, they expand a little bit, right? Usually, almost always. And so its volume's going to go up until I hit the boiling point. But then at the boiling point, I have two things going on. So let's sort of just ignore that one. The mathematicians would say, except for a set of measure zero. One point has zero. A line has a length, right? But one point on a line measured by a ruler has zero length. Let's ignore that, right? Now, if I have that same substance and the temperature is higher than the boiling point, what do I have? You know, I have pure substance A, or a pure substance, whatever it is, and if that pure substance is less than the boiling point, I just have it at a constant pressure, right? But above the boiling point, what do I have? Is it a liquid? No, it's a gas. What's the molar volume of a gas? It's a lot bigger, right? So this curve looks like that. And in fact, you know, it might, I don't know if this is more realistic or not, but let's pretend like it is. Oops. The slope will be different, right? Because if I heat a gas up, it might expand more than the liquid did. So there's a jump here. And that's what I call delta V. So this is sort of a graphical way of looking at what I'm talking about. So as I go marching down this line, right, from A to B, the volume increases slowly. Then there's a big jump, and then I have a new value there. let's draw another picture. I would even ask this question in general chemistry. Can you believe it? But I would draw some pictures, and it'd be a multiple choice. Which one shows the dependence of molar volume on temperature? And I might have one where it just goes straight through. There's no change. Might be one where it gets smaller. So the artistic talents were not required, but kind of knowing what was going on. Let's look at entropy, molar entropy. So I start here, and you know it changes, but we could say roughly it's constant, right? So I put a little change in there. I heat up the liquid, it gets a little bit more disordered, a little bit more, but not so much, right? Slowly with temperature. But then I hit that boiling point. What happens to the entropy? And again, it jumps a lot, right? And so here's this is delta S of that, and I can put since we're talking liquid to gas, right? We could put sub VAP, vaporization. And in the back of the book, there's tables of like delta S of vaporization, you know, delta V of vaporization. Maybe that's not always in the table. But you get the idea. Let's look at the enthalpy. Same story, right? And let's draw our points. And there's some enthalpy, and then again there's a big jump. And this is you know the kind of thing that you looked up in tables. That's the heat of vaporization, right? And remember that graph I drew long ago where I had Q, which is the heat added, and I had the temperature, and I had this sort of piecewise curve, something like that. And if I'm at the boiling point or at the freezing point, the melting point or whatever, I add heat and the temperature goes up, but then I get to this point where I add heat and the temperature doesn't go up. That was that amount of heat I had to add there was delta H, right? So and so here it is on this graph. Now, you don't want to get lulled into a false sense of security. Say, oh yeah, just draw a graph like that and you'll be fine. We can now do the next thing, which is a chemical potential. So what happens to, so I have a chemical potential, let's say of liquid, and I increase the temperature. What happens to the chemical potential? Remember, d mu was minus S dt plus V dP. And P is constant for this process. So if I increase the temperature, dt is positive, d mu is negative, right? And we already drew this picture, and so I have mu as a function of t, and it's going down with a slope that is negative. Okay. Now, when I hit this point, what can I say about the chemical potential of the liquid in the gas? I can't I can't necessarily say much, except the graphs have negative slopes. But when I'm at the boiling point, and let's say I know the chemical potential of the liquid, do I know the chemical potential of the gas? Well, mu liquid equals mu gas, at the coexistence curve. So if I go way back to this picture, and I go along that line, when I hit that point, I'm on the curve mu liquid equals mu gas. So I have to draw I have to draw something here that has negative slopes. The slopes are equal to the entropies of the various phases, and they have and those lines are continuous at the point that I put on that curve. So if I do that, I get this picture, right? So the slope is minus S liquid, and this slope is minus S gas. And so the gas has a steeper slope, but they connect there. Because at this point, mu liquid equals mu gas. Okay? Now here's one. This is the constant volume heat capacity as a function of temperature. Now, so, you know, C sub P is partial H, partial T, a constant P. So if I go back to my H picture, and you know, I tried to draw this accurately. I mean, it you know, varies. But for this example, let's use this. Let's assume this is in fact the case. So there's a positive slope, and the way I drew it, it has a steeper positive slope after the jump. Yes. Oh, yeah. Well, you know, don't listen to what comes out of my mouth. It's constant pressure. Like the heat capacity, C sub P means the amount of heat it takes to change. So if I want to increase the enthalpy by a certain amount, I have to add the enthalpy will go up by a certain. It's that derivative heat capacity, right? And it's sort of there's sort of like the bigger the heat capacity, the more Q you have to add to get the temperature to go up. So, but this is the definition. Constant volume would be partial U, partial T, and constant V. But we're in the chemistry world now, and so we're talking about this picture, and we're working our way along this constant pressure. So if I look at this plot, you know, I have a heat capacity that's that slope, and then I have a heat capacity over here that is a different slope, and it's steeper. So the heat capacity is less for the liquid than it is for the gas, the way I drew this. But what happens right at that point of phase transition? Yeah, I mean, if what's the derivative of that function here? Well, yeah, it's basically infinite. You know, like I could round this, I could smooth this out. Okay, like use some, and there would be a very steep derivative there. So what happens? So we have T sub A, T sub B, T sub B, and here's our T boiling point. And I can put my dotted line. So we come along like this, and then there's a singularity there, and then it comes out the other side. So there's a jump here, right? So the way I drew it in that picture, it's a jump. But this diverges. So the heat capacity diverges at the phase transition. And a lot of theoretical physicists spend a lot of time studying how it diverges. You know, and usually, and this is true for the second order phase transitions too, but oftentimes you'll have something like T minus TC, and this is just a parenthetical remark. T sub C is the critical temperature. That's where things happen, and there'll be some exponent alpha. So, and the, is alpha a fraction, or is alpha an irrational number? Or, mathematical theorems are flying around. But but if you take 1 over something, 1 over 0, right? T goes to TC, so it's going to 0, and the thing goes to infinity. But how it goes to infinity interests people. But basically, the heat capacity diverges because if I'm adding heat, I mean, if you want to kind of see how that comes out, like dH is the amount of heat I have to add, and dt is how the temperature changes. If I'm sitting there at the critical, at the boiling point, I can add a finite amount of heat, and the temperature doesn't change, okay? Because all I'm doing is converting liquid to gas. And that mathematically turns into an infinite heat capacity, okay? So that would be, I don't know. Do you like these? Do you like this question or not? You don't like it, okay? Yeah, okay. And, well, look, like if you do you like going to the dentist? No. Okay. But should you go to the dentist? No. Okay, so that is, well, yeah, you should. But it's much better to go if you have dental insurance than if you don't. So I went for a long time not going to the dentist. When I was taking PChem, in fact, I had a friend in dental school, because there was a dental school at Nebraska, and he was on my dorm floor as a freshman. He was my roommate in some house with a bunch of hippies after that. And they needed laboratory animals at the dental school, which meant that I could go there for free, and this guy would fill my cavities. But this was the same guy that we were recovering from a hangover or something, and his hands are shaking as the drill goes in. This is what. And then it was for a while before I had some dental insurance, and then I went back to the dentist. But anyway, I'm not recommending that as a strategy. Okay, so that's pretty much all I want to say about these phase transitions. There are the second order ones, but I'm not going to talk about that. That's this point here, and it's sort of criminal not to talk about it. But we could spend a lot of time talking about that point and what happens there, but I'm just not going to do that because we have places to go. So we're moving on to Focus 5. It sounds like a 70s disco band or something like that, doesn't it? But really it's about mixtures. Okay, so now we have more than one component. So we have like N1, N2, up to N sub R of mole numbers. So here R is equal to the number hashtag components, hashtag of components. It's okay if I use that thing because it means number, but it's become something else. There's that many components. And so my thermodynamic functions, let's call them state functions, depend on more than one n. So for instance, G, well, it was like for one component, this is what we had, right? And it was n times mu of T and P, and mu equals the chemical potential. And so in this case, mu was equal to G divided by n. And so, it was simple because if I had three excuse me, 3 moles of an ideal gas. I have my G's and my U's and my H's and whatever, A for good measure. And but the molar quantities I just divided by the number of moles, okay? So that was pretty simple. But for R components, I have, it's a function of all the mole numbers, like that. And now, my chemical potential, like mu sub J, okay, is going to be the derivative of G with respect to N sub J, and I hold T and P constant, but I also hold N sub K, and I'm going to write it like this. You know, I'm going to stop doing this, but this means the set of N sub K's where K is not equal to J. So for instance, if I have N1 and N2 and N3, let's say I have a 3-component system, right? So then, you know, mu1 will be partial G, partial N1, and constant T, P, N2, and N3. Okay, etc. So you hold everything else that it's a function of constant, and I could write here J equals 1, 2, ... R. So like if I have 3 components, I have 3 chemical potentials, mu1, mu2, mu3, which are derivatives of G with respect to N1, N2, and N3 respectively. Okay, so the chemical potential is a derivative instead of just being, you can't, you know, and this more general formula works here too. There's only one component. If I take the derivative of N times mu with respect to N, I just get mu because the mu doesn't depend on N, right? So this is the general definition. And I can write my dG as minus S dt plus V dP, and I have another term, which is mu sub J dN sub J, and because and you know this thing minus S is partial G, partial T, at constant P and N's. The V is partial G, partial P at constant T and all the N's. And the mu's are partial G, partial N sub, the mu sub J at constant T, constant P, and also all the other N's constant, except for the one I'm taking the derivative. So it's just it's the total differential of a function, but it perhaps is starting to look a little less pleasant. And so mu sub J is what they call a partial molar quantity. But there's other partial molar quantities too. Like for instance, and I remember, so like I said, those things I remember I'll probably keep talking about. There's something called the partial molar volume, which I did not like at all as an undergraduate because it just didn't make any sense to me. But I could define the partial molar volume of the jth component of something, which is the derivative of V with respect to N sub J. And of course here T and P and N sub K not equal to J would be held constant. And it's kind of a weird thing. Like if it's how the volume of let's have a mixture, okay? And the thing I remember about this is back before they cared about safety in laboratories. So they cared more about money, I suppose. So we were mixing benzene and hexane, okay? Now, is benzene something you should be just mixing? Like you walk in the lab, oh, there's that familiar smell that you start liking it after a while. The smell of benzene is in the air. It's like that movie, Apocalypse Now. I love the smell of napalm in the morning. You know, you should watch that movie if you haven't. I love the smell of benzene when I go into a teaching lab, because we're mixing benzene and hexane. And when you mix these things, so you have a mixture and you have molecules in there, and they interact with each other, right? So benzene interacts with benzene, hexane interacts with hexane, but hexane and benzene interact with each other. So like when you start mixing benzene and hexane, the total volume of the mixture will do some funky things, you know. So there are these quantities that are partial molar volumes, and they depend on the composition. So like V sub j depends on Tp N1 through N sub r. And so we would this many moles of hexene, this many moles of benzene, mix them together, measure the volume, make some graphs, write some lab reports, do some error analysis. You know how it goes, right? So there's a lot of these quantities. I'm not, and the book talks about them a lot more. I'm not gonna go into that too much, but like we have dV would be the sum of over j, v sub j, dn sub j, etc. And you know, like anything you can imagine, we can have a partial molar quantity associated with it and do things like that. But mu is one of these things, and that's the one we will talk about. Now, there is some math here, which I'm not going to talk about. I'm sorry, I apologize for that. Take the graduate course if you want to talk about kind of the mathematical inexorability of what I'm about. Inexorable means it has to be this way because of, it just does. And the fact that these state functions are extensive, and the fact that the math is the way it is means that what I'm going to write here has to be true, but I'm not going to prove it to you. These molar quantities, like it turns out, so see how this dg is the sum of j, u sub j, dn sub j, and this is like if Tp is constant. I have to add this stipulation. If the temperature and the pressure are constant, then that's how the differentials are. But it turns out that V, okay, is the sum of j, v sub j. Whoops, I have to change my font here. Is v sub j, n sub j, and g is the sum of j, u sub j times n sub j. So that's the way it is. Okay, and this has to do with the fact of that the G is extensive. Okay, but we know. Okay, so if T and P are constant, then dg, I know from above here. See this thing here. If T and P are constant, then dg is mu sub j, dn sub j, right? But if I claim that that's G, but Doc Martens claims G is sum of j, u sub j, n sub j. that means that dg is the sum of j, u sub j, dn sub j. But, your calculus teacher told you that when I take the differential, I got to do that, right? Because it's a product, the product rule. But what this tells us is that, turns out, and this is some of the math that's, this is a little glimpse of it, that this is true. And, this actually is an important equation that we're not going to dwell on. We'd have to raise tuition for that, I guess, right? So we're going to leave this out. But you can upgrade and take the graduate course. This is something called the Gibbs-Duhem equation. And what that is, in a sense, is it's a constraint on how chemical potentials can change. You can't just change all the chemical potentials of a system. They have to change in such a way that this is equal to 0. But I'm just mentioning this because it would probably be illegal not to. But I'm not gonna go too much into this. But this is just a glimpse at some of the sort of some of the underlying structure. But let's get back to some more interesting sort of physics, just thought experiments. And let's talk about mixing, okay? So let's say let me draw this. So mixing of gases. And so I have gases A and B. And so I'm going to put A, this will be A. And this will be B. And, the way I drew this is I'm going to have a constant pressure. We could call it P naught. And the temperature is T naught, which is also constant. And the way I drew this is, so I have, I drew four dots on one side and 6 dots on the other, right? So there's 10 dots, right? And I'd have to do the arithmetic, but 2/3, let's see, 4 out of 6. This is one of the volumes is 40% of the other one, so that I have the same volume on both sides of this partition, right? And if A were equal to B, then I'd have something like this. And if the pressure here was P naught and the pressure here was P naught and the temperature was T naught, what would happen if I took out that partition? Nothing, right? And so I take the partition out, and I can put it back in. Now, we were talking about this before the class started. If there's only 10 atoms, they're bouncing around, or I could take the partition out, and I could put it back in. And instead of having 4 and 6, I might have 2 and 8, right? Just by chance. But if I have 4 moles and 6 moles, I take the partition out, put the partition back in. I have a gas with the same thing on both sides. I have a gas with the same stuff on both sides. Pressures are the same. There's no thermodynamic cost. There's no thermodynamic impact of taking the partition out and putting it back in. It's all reversible. That makes sense? Okay? But if they're different, right, then I take it out, then I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Can I put the partition back in? No, no, if I put the partition back in, I've got a different thing. It's not reversible. Taking the partition out is irreversible. And I'm using terms, right? And the gas will spontaneously mix, right? So we want to calculate delta G of that mixing. And how do I do that? Well, there's two ways you could do it. Well, there's probably more than two. And of course it's an ideal gas. And let's say it's monoatomic as usual. But I have n sub A moles of A, and I have n sub B moles of B. Right? So the mole numbers are not one. If let's imagine that I had A on one side and I didn't have any B. Okay, and I took the partition out. Have we done that problem? Yes, right. That would be free expansion, right? So you can imagine looking upon this as you could have two boxes. You could have, and we're almost out of time, so I'll stop. We could have two separate boxes, one with A on one side and a vacuum on the other. We could have another box with B on the other side and a vacuum, and I could take the two partitions out, and both gases would expand to fill the whole container.